Let's use the calculus of variations to derive the equation of motion for a simple pendulum. So I've drawn a pendulum out here in blue, its length L, there's a little pink bob at the end of mass m. The angle that's been drawn up is an angle of theta, and the length here, which is the arc length, is a value of s. Now we know from a conservation of energy that the pendulum starts off with a potential energy EP, and whenever we let it go, it loses the potential energy and gains kinetic energy. So eventually when it gets to the bottom point here, when it's travelling at its highest velocity, the kinetic energy is a maximum, the potential energy is a minimum. So we got this exchange between kinetic and potential energies throughout this process of the bob swinging along at the end of a pendulum. So we're interested in finding out what the potential energy is and what the kinetic energy is. So we know the potential energy from previous videos is going to be given by mass times gravity times height. But what is the height in this case? Well, the height is how far up it's been drawn, the vertical direction. So if we move the pendulum to that point here, then the height we're interested in is this little height here. Okay, so we can get that little height there if we notice that the entire height up here is just the length of the pendulum, length L. So that length there is length L. And we notice that this length here, well, that's just going to be equal to, if we call that x, we would have x upon L, that would be cos of theta. So that length x would be L cos theta. So finally, this height here, delta h, is going to be the length L minus this length here, which is L cos theta. So we take out the common factor of L, we've got L1 minus cos theta. So finally we can say that the change in potential energy is going to equal the mass times gravity times L1 minus cos theta. So that's just done one part of it. So now we're interested in the kinetic energy of the system. So we've got the arc length here, which is s. Now if theta is in radians, then we can say that this length here, s, is going to equal the L times the value of theta. So then we can work out the angular velocity by differentiating this with respect to time. So we'll use the dot notation here because that's what you tend to see when you're doing mechanical questions. So we'll differentiate that with respect to time, so that will be just be s dot would equal L, which is fixed, just the fixed length of the pendulum, times theta dot. So the kinetic energy is going to be half mv squared, but the velocity this time here is going to be the angular velocity, which we've just worked out, which is L theta dot. So the kinetic energy will be a half m, and it will be L squared theta dot squared. So now we've got the two things we were looking for, the kinetic energy and the potential energy. But for calculus of variations, we're looking at minimizing particular quantities. So in this instance here, what is the quantity we're looking to minimize? So remember whenever we did the looking at the shortest distance between 2 points, then it was quite obvious the thing that we wanted to minimize was the path length. But in this instance here, what is that quantity? Well, I'm just going to tell you what it is, and we'll go over it in a future video. So in this instance here, nature works in such a manner that it tends to minimize the difference between the kinetic and the potential energy. So we give the kinetic energy the value k, and we'll call the potential energy u. So nature works in order to minimize the difference between these two. Now that's given a special name, that quantity, and it's called the Lagrangian, and you'll usually just see it written as L. So we can say the Lagrangian for this system is the kinetic energy minus the potential energy. So it's a half ml squared theta dot squared minus mg L1 minus cos theta. So this equation here is the equation that we're looking to form the minimization on. Now don't worry if you sounds a bit confusing if you've not seen that before. We will be going over the stuff on Lagrangians in a future video, and in fact I could fill a whole video series on purely on Lagrangian mechanics. So if you like, you can accept this for the moment and we'll move on with it. So let's take this, and we're going to have to use the Euler-Lagrange equation on this particular equation in order to derive the equation of motion. So let's go ahead and we'll do that on the next slide. So I've rewritten the Lagrangian out here, which we derived in the previous slide. I've also written out the Euler Lagrange in this form here. So from previous videos we've seen the Euler Lagrange is written as partial f by partial y minus d by dx of partial f by partial y derivative. But in this instance here, the function that we're using is not a value f, the function is the Lagrangian L. Also, the variable that we're working on isn't y, the variable we're working on in this example is the angle theta, and also we're doing it with respect to time. So it means we can write partial L by partial theta equals d by dt of partial L by partial theta dot. Now, as we work through more and more examples, you'll get used to picking out the correct variables and getting this into the correct format. So if we look at doing this, we're looking at partial L by partial theta of this equation here. So the only part of this equation that's got dependence directly on theta is this little part, cos theta. So when we differentiate that, we have a minus times minus would be a plus. And this part here would be mgl, which would just be a constant, so that would disappear. And whenever we differentiate the cosine, we get minus sine, so we would end up with minus mgl sine theta. Now we want to differentiate this equation here with respect to theta dot, so the only part of this equation that's got dependence on theta dot is this part here. So the value of the half and the m and the l squared, they're all constants. Whenever we differentiate the theta dot squared, it's going to be 2 times theta dot. So the 2 1/2s cancel out, so you'll just be left with ml theta dot. So now we've got to take this here and differentiate again with respect to time. We differentiate that with respect to time again, our ml squared remains the same, and our theta dot becomes theta double dot. Okay, so now we're left with the two parts of this equation. We've got our ml squared theta double dot equals minus mgl sine theta. So we can say our theta double dot is equal to minus g upon l sine theta. So that's the equation here, and that's a standard equation for the motion of a pendulum. So that's all there is for this video, and I'll get you on the next video. Goodbye.